that those who are time shifting and watching it later have the opportunity to stay up with the series. My name is Bill Gibbs. I'll be the moderator for the session today. It's just a pleasure to have you here. Now, let me just talk a little bit about what this is all about. If you've joined the webinars before, the plugged-in webinars, you know that they're specifically designed for high school and community college transfer students. However, they really are a broad appeal to many people, and we've had many guests join us who are not in high school and far from it, in fact, but I'm glad to have you join us. Now, this is actually the fifth of the 8 sessions that we're holding this fall. Today, October 23rd, we're in the 3rd session of the Robotics Project Certificate Series, and I will talk more about the rest of these that are coming up toward the end of the presentation. This is session 3, as I just mentioned, for the Robotic Sensors and Systems Engineering, and it'll be presented by Dr. Vijay Kotha and Dr. Raj Dasgupta, and I'll be introducing them, or they'll introduce themselves in just a little bit. Here's the agenda we'll be following for today. Now, if you've sat in on any of these sessions before, some of this will be repetitious until we get to the actual presentation. We will talk just a little bit about capital, then we'll talk about the session pointers, the housekeeping as it were, a little bit about the series, and there Dr. Vijay will join us for that. He will also introduce our primary speaker today, Dr. Raj Dasgupta. And then we'll have the presentation, and during the presentation we'll take questions, and we'll also allow for time during the presentation after it for additional questions. We'll end with talking about upcoming webinars, how to get the recording, how to get the slides, how to get a certificate. We'll cover that all at the end. Now, just a moment to talk a little bit about Capital Technology University. I want to make sure I get my notes out so that I say this exactly right. We are a nonprofit, private, accredited university, physically located in Laurel, Maryland. I say physically located because all of our graduate students are actually virtual, that they're attending courses online from all over the world, but we have an actual real campus in Laurel, Maryland. We have both regional accreditation and state authorization from the state of Maryland to offer degrees all the way ranging from associates right up to PhDs and Doctor of Science degrees. We are an award-winning university. Earlier this year, we won the prestigious 2020 SC Media Award for the best cybersecurity higher education program in the United States. Likewise, we was named as having one of the finest master's level programs in the United States. And even though this is designed for high school students, it's good to know that you're involved with a program that has exceptional training and exceptional education throughout the entire scope of whether you want to study at the bachelor's level all the way up to a doctoral level. We are the only independent college in Maryland dedicated to engineering, computer science, information technology, and business. And as I thought about this session today, I realized that many of these are right here in this webinar: engineering, computer science, information technology, and perhaps even a little business is covered in this as you learn the skills necessary to create your robotic project. Here are the session pointers. We'll answer questions throughout the presentation. It says at the end, but in a discussion with the presenter earlier this morning, he would like to take the questions as they occur. Now, you can ask questions in one of 2 ways. The best way is through the chat. Everybody who types into the chat will see the chat, and you will be able to see everybody's questions and type in your own. If you have a question that you don't really want everyone to see, but you want the presenters to see, you can use the question and answer format. But I think that the best one for most of us will be the chat function. Microphones and webcams are not being activated for guests today. We will be sending a link to the recording to all registrants, whether you attend the live session or whether you just simply registered, but we'll make sure that that's available. We'll also put a link to the recording on the on-demand section of the Plugged In Webinars webpage. And we want you to let us know how we're doing. We love feedback. The session will last almost exactly 60 minutes. We will be done by 4 p.m. Eastern Time. With that, I want to give control over to Dr. Vijay Kotha, who is our coordinator for the program. He is going to provide an overview of the entire four seminar webinar series, plus talk about an exciting event that's coming up here at the end of the month. So over to you, Vijay.
Thank you. It's always a privilege to be part of the Capital Tech Talks. As a historian, we want to bring capital to the front. As you may not know, if you had come to the first talk with Leslie, we talked about capital history at the Naval Research Labs. So when Capital was founded, the person who single-handedly built a Master Chief was into distance learning. This was 1920s DC. So he had the vision. And so it's our mission as we volunteers to bring a marker, and IEEE wants to do it, to make Capital the first distance learning center in the world. So again, we have the history, we have the pieces that we need to put together. And that's something that I'm excited about, that we can say Capital has been in distance learning a long, long time ago from its initial days. The things I would like to talk about, the ones you missed, Leslie and I covered a bit of PiMars, a bit of what we expect in students, and then the third one is ethics and privacy. So if you are interested in any of these areas, on the 7th and 6th of November, Sigma Xi, which we are society members of, we have events and it's free. You can come in and listen to Sigma Xi, where neuroscience at the intersects of bioethics, bio-inspiration will be presented. So I'm looking forward to all of it. And of course, we have two other speakers. Steve presented about the mechanical designs of PiMars, and we will be hearing a little bit of systems engineering and sensors. But before that, I want, again, those who are taking this as a part of the certificate to take advantage of the 31st, the Halloween day. We have a physical activity that you can also come virtually, but it's more fun to control robots and planes and possibly trains using a Raspberry Pi. And so Raj will be there. The other mentors from Mazer, Mentors Advancing STEAM Education and Research, we are there to help you. And if you come with your costumes, there's going to be a parade at the Shrom Hill Park. It's an outdoor park from 2 to 4. So the programming is in the morning at 10, and there's lunch and breakfast provided for you. And you get to learn and meet the people who have been part of this activity physically. So it's all fun, and you can look us up in the Greenbelt Rotary, greenbeltrotary.org. And there's a Zoom link, and you can connect it on Saturday at 10 o'clock. So I personally wish you can come. Personally wish you come with your school's best clothes or Halloween clothes and be part of the parade in the evening. So either way, you'll have lots of fun and you'll meet new friends and activities that are associated with programming and learning to code. So our speaker today, Raj, I've known him for a couple of years. Before, when I was an NRL employee, he joined us as a faculty from Nebraska. And he was a computer scientist there, and he got his undergraduate from Calcutta and moved to UC Santa Barbara, where he got his PhD. And after years he loved what he saw at NRL and became a government employee. And Raj is passionate about STEM, and you'll see that in his presentation. It's very interactive, and so we expect you'll be hearing a lot more that you can take advantage of resources at the lab, and we want students to come and be part of the team here. And you can be at Raj's lab at the Naval Research Lab. So with that, I'm going to cede over to Raj, and Raj will control the slides from now on. Over to you.
Thank you, Vijay. Thank you, Vijay. I'm just trying to get control of the slides. Okay, I guess I am in control now. Thank you, and hello, everyone. It's very nice to be here to be able to talk to you. As well, Vijay introduced me. My name is Raj Dasgupta. I am a computer engineer and computer scientist too with NRL, the Naval Research Lab in DC. And today I'm going to talk to you about robotic sensors and how to integrate those sensors onto robots. So the main robot platform that I have in mind is something that you saw in the last talk or last week that Steve Laval was talking about. This is the PiMars robot. Okay, it is a wheeled robot with 4 wheels and just several sensors on it. So my plan is to talk about the sensors and also how to make the robot work, or rather what the robot does with the sensor data. Okay. This is going to be the outline of my talk. So prior to starting, I will just say a little bit about who I am, where I am from. So like Vijay introduced me. Just give me a second, trying to go back to the slide. Anyhow, I'm not sure if I can go back to one slide before, but let me just say, my name Raj. I hail from the country of India. Okay, I hail from the country of India, from the city of Calcutta. Calcutta is on the eastern coast of India, the eastern part. So right there you see a map of India, and the red arrow shows where the city of Calcutta is. So I grew up there, did my undergraduate in computer science and computer engineering from there. And then from my graduate studies, MS and PhDs, I moved to California. I was living in Santa Barbara, went to UCSB, and I show you the campus there, and the red arrow basically shows the lab out there. So it was on the sea beach. It was a nice view, but then grad student life is a very busy life. So basically after 3 months, we were hardly looking out of the window to the nice scenery out there. We were mainly focused on the lab and our work. Subsequently, after completing my PhD, I joined the faculty of Nebraska, and I like to teach. I like to do research there, and I was there for 18 years. And as part of my work there, I set up the robotics lab. It was called Semantic. And we used to do very exciting research on many robotics and AI related topics. And while I was doing that, I mentioned some of the topics out there. Basically, we used robots to find landmines and robots for extraterrestrial exploration and so on. But underlying all of that, I have always had a strong passion for STEM. And so right there, I have put a picture showing one of the STEM fairs that I had been to. And here you can see some students checking out some of the robots that we used to use in our lab. And I have been strongly involved in STEM activities since 2009, so slightly over 10 years. And I am very excited about it. And right now, this activity that I'm doing, other activities that I do with Vijay and his team, like the one that he talked about, Girls Who Code, which is coming up next Saturday, all of these are STEM. And so along with doing research, I strongly believe that it's a very important thing to have younger students, high school students, college students get excited in STEM, get excited in robotics, so that we can build up the next generation of scientists to work on the topics that we are excited about now. Okay. And then lastly, after working in Nebraska for 18 years, last year in 2019, I moved to NRL. And I work in the topic of AI, game-based AI, game theory, machine learning, and so on. All along, robotics has been one of the major themes. Even the work that I'm doing at NRL right now has robotics as one of the streams. And so today I come to you to talk about robots and sensors. So here you see the picture of a wheeled robot. It's a 4-wheeled robot, much like the PiMars robot. So when you have a robot like this, a robot that can move around, there are 3 key questions the robot has to answer or ask itself. which is where am I now, where am I going, and how do I get there? And typically the robot, in order to answer this question, typically the robot will work in the same way that we humans do, which is, for example, we'll look at a map. If you have a phone, you take out your phone, you turn the map application on, or if you have a GPS on your phone, you look at where you are located now, and then you look at the map and chalk out a path about how to get to where you want to reach, and then you just follow that path. So that's the same thing that the robots do. And the first step of that is to understand where am I? And then while we are walking, we of course don't want to bump into things in our way. We don't want to bump into other people that might be on the street. We don't want to bump into like signposts or maybe lampposts that are on the street or any other obstacles on the way. And to do that, we look around ourselves. And that's exactly the same thing the robots do. While they're moving around, the robots have to avoid colliding with obstacles. And that's the main reason why robots use sensor. While robots are moving around, they do not want to collide with obstacles. And so basically to avoid collision, robots have sensors on them. So they help robots to sense what's around them. And this is very similar to what we as humans do. As you know, we have 5 senses on us, right? We have the sense of sight, we have the sense of hearing, sense of smell, and so on. So similarly, similar to our sense of sight, what does the robot have? Robots have a camera on them. So this is the camera of the PiMars robot. And you must have seen robots. If you have seen robots, you must have seen several robots have cameras on them. It's a very widely used sensor on robots. We are going to talk about the camera sensor today as well. But apart from looking around with the camera, there is another large set of sensors that the robots use, which we as humans don't do. We typically use our eyes to figure out. And what we do with our eyes, when we are looking at objects, our eyes, basically we have a pair of eyes. So we have stereo vision on the eyes. And that allows us to understand the depth of the field, which is how far the objects are to us. Robots also use a large set of sensors to find the depth, or what is called the range, which is how far is an obstacle from me. Right? So they don't always use, or they don't essentially use the camera for that. They use other types of sensors. So some of the sensors that we'll talk about today, like the infrared sensor, or mainly the ultrasonic or the sonar sensor, they are basically a range sensor. On the PiMars robot, this is the ultrasonic sensor, the one on the front with those 2 circles on the front. Now, once the robots have sensed, then the next thing, like humans, is to take action. Like for us, if we are moving around, we use a map, and then we use our legs to walk around. We use our hands to move objects. The robots do that. The step for robots for doing that is called actuation. Here I have given examples of 2 robots, and you can identify the sensors and actuators that are on them. On the next slide, I show another robot. This is a tabletop small robot that I worked with for nearly 15 years. It's called the e-puck because it looks like a hockey puck. And on the slide out there, I have marked in red font the different sensors that are there and a couple of actuators. Like you can see, it has wheel actuators as well. It has a speaker as well. But the red fonts basically show the sensors. So as you can see on the front, it has got a camera sensor. It has got an accelerometer on it, which basically gives the heading or the angle that the robot is facing. And we will talk about accelerometers today too. It has got infrared sensors, which are the range sensors or depth sensors I was talking about. Lets the robot figure out how far it's from obstacles. Just as we hear, the robot also has microphone sensors on it, which allows it to hear sounds around it. And finally, it has a wheel encoder. We will not talk about wheel encoders much today, but many of the less expensive robots have a wheel encoder on them. Basically, what a wheel encoder does is it figures out how many turns the wheel is making. And basically from that, you can find out what is the distance the robot has traveled, and also you can figure out the speed at which the robot is moving. So it is a very low-cost sensor by which you can find out the speed and the length or the distance that the robot has traveled. Here are a few other sensors, few other robots, and I will let you identify any sensors of them. If you want to type any of the sensors that you see on the robots, feel free. I will give you a second to look at them, and then I will talk about briefly the sensors on the different robots. Okay. So on the leftmost picture, this was the EPUC robot we saw on the last slide. This is another custom built robot which I used in my lab. And this has got a rain sensor. It has got a laser sensor on it. Today we will talk a bit about laser sensors. This is another custom built robot we had in our lab. It's once again, it's an outdoor or all-terrain robot, basically, a rugged robot. And this one is fitted with a metal detector on it. So basically, it's a sensor to find landmines or find metal objects buried under the ground. This robot, this is called the TurtleBot robot. And this TurtleBot robot used the Kinect sensor. So you can see there's a laptop right on top of the robot. And right below the laptop, you can see Kinect sensor. So Kinect sensor is another rain sensor that is used on robots. And finally, the UAV has a camera. It has an accelerometer on it. And it has a couple of other sensors on it as well. But the camera was the main sensor. So that's to give you an idea of how different robots look like and what sensors there are on them. Okay. So at this point, let me, from the next slide, we will get on to the specific sensors we are talking about today. But let me mention a couple of things to you at this point, which is first, I always welcome questions from you. So as I'm talking, feel free to interrupt me, or in case you don't have audio communication, feel free to use the chat box to type questions, and I'd be happy to answer them as we go on through our talk. Also, I have tried to give information about the three sensors that we are going to talk about today. So I have quite a few slides giving the concepts underlying the sensors. Also for one of the sensors, the IMU sensors, which is basically the accelerometer and the gyroscope sensor, I have given a little bit of code. So the reason for telling that is we might not have time to delve into each of the topics, but the slides are available to you. So feel free to come back to the slides anytime, check them out. And if you have any questions afterwards also, I'm available via email. My email is given on the last slide of this slide deck. Feel free to get in touch with me via email if you have any questions. Now I work for the Navy, and on the Navy, we mainly work with ships and submarines. And on the ships, there are an array of sensors that are used. So these are some examples of common sensors. You have depth sensors, you have level sensors, you have tank level indicators on the ships, a wide array of communication sensors, radar, and so on that are available, flow switches on the ship. And so this is just a smaller diagram. On the next slide, I'm showing an actual patrol boat that's used by the Navy. And you can see the wide array of sensors that are used on this. There are several sensors, several types of electronics devices that are available on this, on an actual patrol boat. Essentially, the array of sensors that you have on modern robots or modern systems is vastly complex. So basically what a robot does is it does a sequence of things, just like humans do. They sense, they plan, and they act. Okay. So for the first step of this is the most important, which is sensing, which is understanding what's around the robot. And historically, initially sensing was done with planning and acting, but that proved to be too expensive to do because computers were very slow in the 1960s and 70s. So basically researchers took out the planning cycle from the robot, and they basically had the sense and act. This is how, if you have seen the Roomba robot, the vacuum cleaner robot, this is how Roomba works. Basically, it has got a bump sensor on it. And when the bump sensor goes and hits an obstacle, basically it tells the robot to act, which is it backs up a little bit, turns at a different angle and goes. So it's very simple reactive behavior of the robot with its sensor. But these days, over the last 2 decades, as computers have become faster and smaller, so the plan cycle again has been put back into the robot. So basically what is done now is basically we are able to collect tons and tons of data for the robot. And so the planning many times is done offline. So it's called pre-planning. And then once the robot has completed the plan, while the robot is working, it senses data, it falls back to the plan that it pre-calculated, and then it reusers that plan in order to take actions. So at this point, let me talk a little bit about the internship opportunities. Most of the audience today is college students, and we have an excellent summer internship program available at NRL and other Navy centers as well. It's called NRIP. It's a 10-week paid internship. It pays quite well, not too bad, I should say. And you get an opportunity to work on cutting-edge research topics with several researchers in the lab. There's a wide array of topics at NRL that we're interested in. I work in computer science, AI, a little bit of robotics. There are several streams of engineering that are of interest at NRL, and there are a wide array of science topics like radar, plasma physics, acoustics, chemistry. Some of those I have put on there. Feel free to check out NRL's website to find out the topics that the scientists and researchers work on at NRL. Keep in mind that the application is due by the end of next month. November 30th is the application headline. And there are certain requirements like to work at Naval Research Lab, applicants must have citizenship of the US. And then undergraduate applicants need to complete at least 31 credit hours to be eligible to work. And for more information, I encourage you to check out the website nrip.ace.org, and that gives all the application requirements. I hope some of you will be encouraged to apply for this. With that, let me get into the meat of our talk. I will briefly talk about the main sensors, and as I said, we can delve into the details of each of the sensors later on as regards. So first, let me talk about range sensors. Okay, range sensors tell a robot how far obstacles are from it. These are the most commonly used range sensors. As you see the first picture, there is a sonar or an ultrasonic sensor. As I said, this is the ultrasonic sensor on the PiMars Robot, ultrasonic sensor. So let's see how an ultrasonic sensor works. So an ultrasonic sensor, this is how bats used to find obstacles as they fly. Okay, so this is also called sonar. The technique is called echolocation. So the way it works is there's an emitter that sends out a sound wave, and the sound wave hits an obstacle and it reflects back from the obstacle. And then the receiver receives this sound wave back. And basically you can calculate, basically the robot can calculate the distance to the obstacle using this equation out here, which is the speed of sound V multiplied by the time it took for the signal to come back over 2. And that basically gives the range or how far the obstacle is. This is the same concept that is used by ships in order to find how deep the seabed is. These are some of the specifications of the ultrasonic sensor. So basically the range is between 12 centimeter and it can go up to 5 meter. The accuracy or the resolution is up to 2 centimeter, and there's a little bit of error. And basically depending on the frequency of the signal that you sent out, the range will change. So basically if you have a high frequency audio signal, you can get up to a higher range. For the sensor that we have on the PiMars Robot, the range is up to the smaller range, the lower range is 20 centimeter, and I have tested with range up to 2 meters and 3 meters. So it works up to this range. I wish I was able to show you the working if we had been in a live session, but we have everything working on this one. And basically if you bring your hand close to it, you can see, and if you move it back, you can see that the range value that it sends back changes. Okay. Now let us talk a little bit about the limitations of this ultrasonic sensor. Well, first, let me talk about the advantage. Advantage is it's a very lightweight sensor. It's very easy to put on the robot. And it's also very cost effective. It costs hardly $5 or $10 for the sensor, $5 or $10. But the cost effectiveness and the lightweight comes at a certain cost as well, which is, first of all, the field of view, how wide it can see is very narrow. So it goes from 20 degrees to about 30 degrees or 40 degrees. So that's a very narrow field of view that you have. And then the other problem is that if the signal, the audio wave hits a soft surface, like a cloth surface or a fabric surface, basically the sound wave is absorbed by it. and essentially that obstacle cannot be found, cannot be detected by this sensor. Other problem is the audio signal, the sound signal that is sent out, that must hit the object at right angles. So basically, if your obstacle is at a certain angle facing you instead of exactly at right angles, if it is a certain angle, then basically the sensor reading that you will get won't be accurate. Similar situations are shown in the picture out here. Basically, if your robot, if your sensor is facing a corner, your audio, your sound signal can bounce off two walls at the same time, which gives error in the readings. So these are some things, some limitations that the sonar has. But all in all, it's a very cost-effective and low-cost sensor. Now, compared to that, the next commonly used range sensor is the laser sensor. All of you all know what lasers are. And these are two commonly used laser sensors that are used on robots. One is the SICK laser, another is from a company called Hookyu. So the laser basically works on the same concept as the sonar ultrasonic sensor works. But instead of an audio signal, instead of a sound signal, it will use a laser beam as a signal. Another difference is that instead of looking at the time of flight, which is the time that it takes for the signal to hit the obstacle and comes back, basically laser looks at the phase shift. There are some advantages of laser as well, which is the beam is much wider and its angle is also much wider than the sound signal. So basically you can sweep a much wider angle. So most lasers, they have a 180-degree sweep as compared to the 20-degree beam that the ultrasonic sensor had. So you have a 180-degree sweep. Some lasers also have a 210 degrees. So you can also see some ways at the back of the robot. Some lasers also have a 3D, up and down sweep. So basically you can get a wide angle swath. So you can get a view of what is in a wide range around the robot. So on this slide, I am giving the specs of some of the commonly used sensors. So this is one of the sensors, the SICK laser. This was actually the Hookyu sensor we had mounted on one of the robots. And these are the specs of it. So mainly you can see on the last bullet that this sensor does 180-degree scans 75 times per second. So that's much faster than what you would get with the ultrasonic sensor. At the bottom, I show a commercial laser sensor that is used on the Google cars, or at least they used to be used on the Google cars. Many of you have seen the Google cars on the streets that used to construct the Google Maps. And many of these self-driving cars, Google's car and other companies' self-driving cars too, they use this sensor that is called that is made by the company called Velodyne. And basically this adds a 3D sweep also to the sensor movement. And you can see from the specs that its accuracy is very high. Its range is also pretty large. So it has a range of 50 meters. The upper range is 50 meters and the closer range is, I think, a few centimeters. And its accuracy is 2 centimeters. So a very accurate sensor as well. So I wrap up the discussion on range sensors with a comparison of sonar versus laser. Okay. So basically, ultrasonic or sonar is much slower than laser. I give the data out here. So basically, you can compare the speed of sound and the speed of laser. And you can see that laser is 10 to the power of 6 times faster than ultrasonic sound or sound signals. So what that means is what I say on the last two slides. Basically, the time that you have for reacting in laser is much lesser than you have for ultrasonic. While that accounts for much higher accuracy and precision, one of the requirements that you have is that the electronics that you have for the laser sensor has to be much more accurate, and accuracy comes at a price. So laser sensors are much more expensive. Laser sensors easily go up to $1,000, $2,000, and things like that. And some of the more accurate sensors are about $5,000, $10,000, and so on, as compared to $5 or $10 for the ultrasonic sensor. So you get very accurate ranging with laser, but it comes at a price. Lastly, the Kinect sensor. Once again, this is also a range sensor. Some of you, if you have encountered the Xbox, it used to come with this Kinect sensor. And this is also a rain sensor. I have given the specs out there. Okay. At this point, I would like to pause for a few questions. If anybody has questions on the chat window, I would be happy to take them. Okay, then we have about 10 to 12 minutes left. In that, let me talk about the IMU, the Inertial Measurement Unit Sensor. Okay, trying to go one slide down. Okay, so this is the IMU sensor that we have on our robot. You cannot just see it directly here. It's under the board somewhere. But basically on the slide, I'm showing the exact sensor that we have, exact IMU sensor on this. It's the MPU 6050 board. And basically inside the IMU sensor, the two main components that you have is a gyroscope and an accelerometer. So the gyroscope essentially gives you the heading or the angle that your robot has, and the accelerometer, as the name says, it gives the acceleration of the robot, acceleration of the sensor that is attached to the robot. And from the acceleration, you can integrate that amount over time and find the speed. And once again, you can integrate the speed and find the distance that the robot has traveled. So let us go a bit into the concepts or the principles underlying each of these sensors. So first I talk about the gyroscope. So essentially, as the picture shows out here, this is a mechanical one. So there's a rotor at the center of it, which moves at a very high speed. And then you have two gimbals around it. So basically, the idea of having the gimbals around it is that you decouple the force that the central part has from the outside. And basically, that allows you to calculate or keep the central part fixed and calculate the angle at which it is phased right now. So basically, it allows you to find out the heading of the sensor and essentially the heading of the basically the angle at which it is facing. And of course, the MPU 6050 is a very low cost. Once again, it comes for about $7 to $10. And once again, as far as gyroscopes go, the sky is the limit. You can have very expensive gyroscopes as well. Next, coming to the accelerometer, we first talk about the mechanical accelerometer. It looks like this. So basically, you have a mass with a spring and a damper attached to it. And so when the sensor moves, when this accelerator moves along with the robot, basically the mass undergoes acceleration due to the motion, and the mass along with the spring moves. And basically, you can apply these equations out here to calculate how much the acceleration that is faced by this mass is from the constants that are there, from the constants and from by how much this spring has moved. That is the value x, which is the amount of movement that the spring has done. So that's how mechanical accelerometer works. And basically, this is some more information how the Earth's gravitational pull makes the accelerometer move. And this diagram basically shows a single axis accelerometer. The chip that we have that has a 3-axis accelerometer. And basically, you mount 3 of these at right angles or orthogonal to each other to get a 3-axis accelerometer. Now the accelerometer and gyroscope that we have inside the sensor, that is a MEMS-based accelerometer. So instead of just mechanical parts, it has some electronic parts inside it. So this is the construction of a MEMS accelerometer. Once again, it is a spring, it has a mass inside it. And along with the damper, it has got a capacitor inside it. So basically the capacitor checks how far or what the acceleration of the mass is. And basically when you put these two components together, the gyroscope and the accelerometer together inside the IMU, this block diagram sort of gives the steps that you have to do in order to find out how much the acceleration is, how much the speed or the velocity is, and finally how much the position or the distance that's traveled by the robot is. I have given some code later on, and we probably won't have time to get into that. But later on, I presume some of you will be able to use this PiMars robot. So all of this code runs on the Raspberry Pi. And so basically with that code, you'll be able to find out the acceleration and the heading of the robot. And from that, you can find out the speed and the distance that the robot has moved. Now, before we move on from IMU, there is one topic or one issue that you need to keep in mind, which is IMUs basically are very sensitive to errors. So in fact, in this one, the gyroscope that is on the IMU 6050, if you use that to find the heading, you will see that even a little movement of the robot that causes the headings to fluctuate a lot. So basically what you need to do along with the IMU, you need to use a software component, which is called a filter. Very commonly used filter, there are many filters available. Very commonly used filter is a Kalman filter. So basically so in very layman's terms, what a filter does, it basically, it looks at the past values that the sensor has accrued, and basically it smooths the current reading over the past reading. So basically, if you have a lot of ups and downs, if you have a lot of fluctuations in the data, basically what the filter does is it smooths out the fluctuations that might be on the data. Okay. And another issue on IMUs is that the gyroscopes that is there in the IMU, that might have some drift in them. And basically accelerometer data, we saw that with the acceleration that we get, we integrate over time, and integrate it twice. First to find the speed and twice to find the position. And basically every time we integrate, if there was some error in the readings, these errors end up getting integrated and hence getting amplified. So basically after a long period of operation, all IMUs drift. And so basically some external reference has to be used to compensate for the drift. So here I was showing some code which allows you to program the MPU with the IMU with the Raspberry Pi. Okay, since we don't have the Raspberry Pi and because this is not hands-on, I will skim through that. And if you have a Raspberry Pi accessible to you, feel free to check that out. And once again, happy to answer any questions. Okay. Now, towards the end, I said that IMUs have drift on them. So one of the things that you have to do is to calibrate from time to time. Of course, you cannot recalibrate while the robot is working. So one of the techniques that is used to calibrate is you use some ground reference. Okay, and one of the common ground reference that is used is what is called a beacon. And beacon, basically, if you come to the PiMars lab, which Vijay runs, you'll be able to see that there's a setup there that has got some beacons placed on it. So beacons are basically ground locations which have a fixed location on them, and you can calibrate any sensors. Basically the robot, it's a well-known point. So when the robot goes closer to that, it knows where it is. So here I'm showing a device that we used on one of our robots to act as a beacon on the robot. It was made by a company out of South Korea called Hagisonic, and its name was a Stargazer. And so basically it was a fixed location, and it used infrared rays along with stickers. So this device that you see out here, the camera that you see, that was an infrared camera. And the ring that you see on the side that used to shoot out infrared beams. And we used to have these stickers stuck on the ceilings or on the walls of the space that we had. And basically these stickers used to reflect the infrared beams back. And associated with each sticker was an XY coordinate of the sticker. So by looking at the beam, then the camera at the middle, the infrared camera at the middle could understand which location the robot was under, and then it could tell the robot that this is your location. Okay. But once again, beacons are quite expensive. So this device was about $1 grand about 10 years ago, and it's slightly more expensive now. Okay. Finally, quickly, I want to talk about camera. And there's a whole field of computer science and artificial intelligence, which is called computer vision, that deals with the study of image and vision on computers. Computer vision is not an easy problem. So for example, here we are saying that chess might be an easy problem. And chess, as you know, chess was not a very easy problem till about 20 years ago. But chess is a relatively easy problem. But for a computer or for a robot to look at a scene like this and to understand that while driving in it, there's a ball and there's a child coming after the ball, and then to understand that and to stop, that is a very hard problem for the robot. To understand some of the issues, our eyes are actually very good sensors. On the other hand, the cameras that you have on the robot, no matter how expensive cameras you have, they are very sensitive to light. Why is that important? Suppose you have a self-driving car. You train the car to look at the images around it on a bright and sunny day. The next day, you put the car to test. The day is cloudy. The robot algorithm that you have trained cannot make any sense out of what it's seeing. Why? Because it was trained on a sunny day. Similarly, if you have snow on the ground, but you have trained it on a bright, snowless day, once again, the computer cannot understand anything. The robot cannot understand what it's seeing, and itself cannot drive. So computer vision is a very hard problem. Just to illustrate to you, let me ask you, you are seeing the picture out there, which has a grid, a checkered grid, and there's a green cylinder. So which square out there, A or B, is more bright? Well, you can look at it, and by looking at it, our eyes are saying, well, B is white and A is gray or A is dark. So surely B is more bright. Okay. Now let us see what the tricks our vision eyes play. Let's put two bars on top of the green cylinder out there. And as you can see, I have not changed the squares out there. I have not changed the checkerboard. But now, as you can see, due to the tricks our eyes played, A and B, they are both the same color. Basically, they are both the same brightness. Another example. This is a very common example. There are actually no black dots out there. So there are only white dots. But if you look at it, especially if you move your eyes around, you can see some ghost images of some black dots out there. So these are some of the issues that computer vision has to deal with. And as I said, computer vision is an entirely different field. There's a subfield of machine learning called unsupervised learning that is used a lot in computer vision. And one of the fundamental tasks that you have to do in computer vision is to understand where the objects are. And to understand where objects are, you first have to understand the outline of the objects. And how do you find the outline of objects? You basically see where there is a change in color, where there is a change in intensity of the picture that the computer's camera is looking at. And then you can cluster together the pixels that have the same intensity, and that basically gives you one object. So basically, as I was saying, the field of machine learning called unsupervised learning has got some algorithms that allows you to do that. That field is too deep to go into in a few minutes, but just to tell you that there is this large field out there that allows robots to use cameras. Now I have 2 or 3 minutes left. I will just quickly talk about one of the sensors that we used. And this is paired with a camera. And this is not a sensor, basically this is a sensing device. So this is similar to the passive tags or the beacons that I was mentioning a few minutes ago. So this is called the augmented reality tag. It's very similar to the QR code tags. I'm sure all of you have seen QR codes. So they're basically a code, you scan it with the camera of your phone and it leads you to a website. So that's the same principle that is used here. These are called April tags. And so basically what you can do is you can have a camera, robot's camera looking at this. And then inside the robot, you run a program which allows it to make sense or parse these tags. And basically then you can encode information into these tags. So for example, one of the applications we were using a very cheap, lightweight UAV. And we were using the camera on the UAV to look at these tags. And then inside the tags, we were telling the UAV to either take off, go up, go left, go right. I would like to show a video of that now. So if somebody could give me control of the video of the screen.
Okay, I've taken it off screen share so that you should have the ability to share your own screen now.
Thank you. Okay. So here I'm showing a video of one of my former students And what we are trying to do here is we have this quadcopter out here. Quadcopter has a forward-facing camera. And basically, you will see that the student will first show the tags, and then we'll put the tags on a screen, on a wall, and then the robot, instead of explicitly giving commands to the robot can autonomously follow the instructions on the tag. So what he has done just now is he has shown the tag to take off, and it is up. And now he will show the tag to land. And once it sees on the camera, and you can see the screen on the right-hand side, it saw and it lands. And so next what we are doing is we are putting similar tags on a white screen, and then the robot with a camera, UAV quadcopter, takes off. And you can see that the view from the quadcopter camera as it takes off. So the red square shows where it's identifying those tags. And basically inside the tag, inside these tags, it says increase the height of the quadcopter. And out here it says go to the right. And so that's what it keeps on doing. And we have different sweeps of this. I want to fast forward this video and show that there can be many applications of this. For example, you can stick this. For example, one of the projects we were doing with this was to stick these tabs on a warehouse shelf. For example, you have seen those tall shelves that you have in Walmart and Home Depot and so on. And basically, there are people who have to climb onto tall ladders and take stock of the things on top. So instead of that, you can use a UAV for that. And the UAV could follow. You could stick these tags on the side of the beams, and basically the UAV could then parse those tags and figure out where it has to go next, and basically count items. This could also be used for structural inspection, and that's one of the applications we were looking to use this to. For example, if you have a tall central tower, it's very risky for humans to get onto the tower. So if you can put these tags on the tower, then a UAV could then scan these tags and autonomously scan the surface of the tower, and that would make it much safer for humans to do those risky tasks. So we are right about at 3:52. So I would like to just say that if you're interested, there are many videos of different sensors. So for example, here I'm using computer vision. And here there's a robot that I'm putting inside the small intestine of a pig, and basically using computer vision to guide the robot. So there are many applications beyond wheeled robots that we can use. We talked about some of the sensors today and how to integrate them. So I hope I have been able to tell something to you about sensors and how they operate and some applications. So we are right about the end of time now. I will quickly bring you to the last slide and basically give my information out there. And
okay, I think you need to stop screen sharing, and then I will start it up again.
I've done just that. And Bill, if you could just take us to the last slide where I give my information. I would like to put that up. Yep. So my contact information is there along with my email. So we talked about different sensors. And so the bottom line is more accurate sensors means higher costs, but less effective sensors are good for robot fighters. If you have any questions, I would be happy to take them over the chat room.
Thank you, Raj. And again, we are here to help. And what Raj did not mention is this program called NREP also exists for high school students. It's called CAP, CAP.asee.org. And the deadline also for that is November 30th. So if you're a junior or a senior in high school, you get around $3,000 or $4,000 for spending a month and a half at the labs. But the key here, you're going to have moments in time that will change your life. So spending a time with a mentor and doing an internship. Again, Mazer is a nonprofit. Our job is to connect the dots. And so we have lots of mentors. And after this, we have the girls that code on the 31st on Halloween. So come with your dresses. And on the 6th and 7th, we have Sigma Xi And all our mentors will be at the Sigma Psi meeting, and you all are welcome to be part of it. And as you do your journey in science and engineering, we want ethics, privacy, all to be front and center. And we as mentors are there to help you guide with robotics, but more for mentorship. So I'm going to give the control back uh, to Capital. Thank you.
Thank you.
All right. Well, thank you very much. And for those of you that will be watching this online, as you know, on demand, make sure that you notice the email here so that you can reach back out to Raj and discuss this more with him. This has been a very fascinating presentation. I was just thinking there at the very end when you were talking about robots within the human body. Just the other day, I had an opportunity to talk to a medical doctor who does hernia operations robotically, manages that process. And this is something new to me, that a robot would actually be inside the body repairing hernias. An amazing advancement in my mind. Let's go ahead, and I appreciate our presenter and his ability to stay right on time, so I want to make sure we respect that. Let me talk just briefly about what's coming up. We have October 30th, which is just next week. We will complete the series, session 4 of the Robotics Project Certificate Series. And this one will talk about program and visualization. It'll be a great ending to the session. And on November 6th, Dr. Ian McAndrew will talk about why is the sky blue. He'll go into the physics behind that. And then on November 13th, we have one of our recent graduates who is an expert on unmanned autonomous vehicles, who will be talking about the future of these UASs and how they're all going to work together, not just cars, but some of the other modalities as well. If you want to join us for that, look at how to register at captechu.edu/webinar-series. A recording link will be sent to all registrants. We have a number of people who are not able to join us today for the live session, but I'll make sure that they all get an email. And Vijay, if you would also send me the information about both the event on Halloween and also the event in November, I will make sure that all on-demand viewers get that as well. If you attend all 4 of these sessions, either live or on demand or a combination of both, you will earn a robotics project certificate from Embry-Riddle. And of course, you can enter your robot if you've made one in the competition that's coming up here in just a few days. We have 2 upcoming webinars in the CapTech Talk series. The series that we're doing today is called the Plugged In series, but in the CapTech series, I just wanted to mention that they're coming up. For more information, you can visit the website again. One is on vulnerability management, excuse me if I didn't say that right, and the other one is a brand new program going to be offered by Capital beginning in the spring, where if you have an apprenticeship, you can convert that apprenticeship into college credit and move toward a BS in professional trades administration. A very exciting new program for those that are in those trade fields. This does conclude the webinar. We are right almost exactly at 4 p.m. Watch for an email from me within the next 24 hours that will contain a link to the recording and information about the next webinar. And if EJ gets this information to me, I'll either send that as a separate email or I'll send that as part of that email as well. But it's been a great pleasure to hear Dr. Dasgupta. It's been a kind of a mind-blowing, and before we end, I had a question, if he can pop in again. When you were doing landmine detection, how did you correct for drift? So, because you would not want to go over a landmine field and miss big sections of it because of drift. So I was just curious, as we end, what remedies or remediations there are to make sure that every landmine, the entire plot of land was covered.
That's a very good question. And that was one of the main issues that we were trying to solve there. How do we make sure we haven't missed a mine, or what is called basically false positives and false negatives? How do we avoid those? And the way we got around that is we didn't use a single type of sensor on the robots. We used an array of sensors. So you saw a metal detector on the robot. We also used GPR on the robot, which is a ground penetrating radar. We had heat sensors on the robots. So basically, once we used several sensors, that could pinpoint exactly where the landmine was or where the
So,
interest was.
so multiple sensors and multiple expensive sensors.
Yeah, that's true. The
Yeah.
more accuracy comes up.
Right. The more, at least more accurate, if not more expensive. Okay, good. Well, thank you. That was very interesting. That I found the talk to be very informative and interesting, even though I'm not an engineering student myself. All right. Well, thank you very much. And this is the last call. I see that we have no further questions. We do have a positive comment in the text chat from Charles Vergers. I appreciate that. With that, we will officially conclude. It's time right now. And again, watch for that recording and a link to additional information that we'll be sending your way very soon. Thank you very much to both of our presenters for a delightful presentation this afternoon. And with that, we are officially done, and I will stop the remote and you may log out at any time.
Thank you. Good.